Hello, in this lecture we'll find out the radius of the circle using two different methods. In the drawing we have a circle. The center of the circle is at this point O. Line segment AB equals to 6 units in its length. Line segment BC equals to 13 units, and line segment AD equals to 18 units in its length. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees. And our mission is to find out the radius of this circle. So we'll start with the first method. In the first method, from point C, we will go perpendicular on AD. This is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. By doing this construction, we created quadrilateral ABEC. Inside quadrilateral ABEC we have 1, 2, or 3 right angles. The sum of 3 right angles is 90 times 3, 270 degrees, plus this fourth angle. In total, the sum of the 4 angles in quadrilateral ABCE must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth angle must be equal to 90 degrees. In order to complete the sum of the angles in quadrilateral ABEC to 360 degrees, the missing angle must be equal to 90 degrees. Therefore, inside quadrilateral ABEC, we have 4 right angles, and therefore quadrilateral ABEC we relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side EC. But it is given us in the question that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side BC equals to side AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. And what is the length of line segment ED? The length of line segment ED is AD minus AE. AD is 18 units, AE is 13 units, so AD minus AE is 18 minus 13, that is 5. In the next step, we will join points D and C together by a straight line. By joining points D and C, we created here the green right small triangle EDC. In the next step, we'll implement the Pythagoras theorem in the green small right triangle EDC. According to the Pythagoras theorem, here by PT is a relation from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle EDC is DC, therefore the square of the hypotenuse is DC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC squared plus ED squared. So for note that according to the Pythagoras theorem in the great triangle EDC, DC squared equals to EC squared plus ED squared. So DC squared equals to EC squared. EC equals to 6 units. Therefore EC squared equals to 6 squared, 36. Plus ED squared. ED equals to 5 units, therefore ED squared equals to 5 squared, that is 25. In conclusion, we found out that TC squared equals to 36 plus 25 is 61. TC squared equals to 61. Here we take out all of this equation and we will get the DC equals to the square root of 61 units. So we found out that the hypotenuse DC of the green triangle EDC equals to the square root of 61 units. In the next step, we join points B and D together by a straight line. By joining points B and D, we created the right triangle, triangle ABD. We'll implement the Pythagoras theorem on the right triangle ABD. Again, by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus AD squared. So in conclusion, we found out that in the right triangle ABD, according to the Pythagoras theorem, BD squared equals to AB squared plus AD squared. So BD squared equals to AB squared. AB equals to 6 units, therefore AB squared is 6 squared, that is 36, plus AD squared. AD equals to 18 units, therefore AD squared is 18 squared, that is 324. In conclusion, we found out that according to the Pythagoras theorem in the right triangle ABD, BD squared equals to 36 plus 324 is 360. So BD squared equals to, we substitute 360 by 36 times 10. Here we take out all of this equation and we get that BD equals to the square root of 36 times 10. So here we'll take a root, we'll take 36 out of the root. The square root of 36 is 6, and we'll get that BD equals to 6 times, inside the root we left only with 10. 36 times square root of 10. So the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. So right here, we are going that the hypotenuse BD equals to 6 times square root of 10 units. In the next step, we find out the area of triangle BDC. We find out the area of the green triangle, triangle BDC. So the area of the green triangle, triangle BDC here the squared brackets is the sign for the area. It means the area of triangle BDC. It will be equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle, triangle BDC is equal to the base we choose the base of triangle BBC as BC times the height to the base over 2. In the next step, we will find out the height to the base. In order to find out the height to the base, we will extend side BC of the rectangle BDC by a straight line, and from point D, we draw perpendicular on the extended BC. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point D and the extended BC is F. Here, DF indeed creates 90 degrees with the extended BC. Here, this angle equals to 90 degrees, and this angle equals to 90 degrees. Therefore, DF is the height to the base. So, created a quadrilateral ABDF. Inside quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABDF that has 4 right angles, we will relate to it as a rectangle. So I write it down. or the other ABDF is a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle ABDF must be equal to each other. That is to say, side AB equals to side DF. AB equals to DF. But it is also given us the question that AB equals to 6 units. So we can write here that AB equals to 6. And from this equation 6 equals to AB equals to DF. We derive that DF is also equals to 6 units. DF equals to 6 units. Here DF equals to 6 units. That is to say, the I to the base equals to 6 units. Now we can easily find out the area of the green triangle, triangle BDC. So the area of the green triangle, triangle BDC equals to the base of the triangle that is BC, and we know that the base BC equals to 13 units. So we substitute the base by 13 times the I to the base. We just right now found out that the I to the base is equal to 6 units. So we substitute the height by 6, all divided by 2. So the area of the green triangle, triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So, therefore, the area of this great triangle, triangle BDC equals to 39 square units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So this will be rule number 1. According to rule number 1, if a triangle ABC is blocked or inscribed by a circle, so we actually have a circle and the center of this circle is at this point O. And we have triangle ABC that is blocked or inscribed by this circle. So here we have triangle ABC. This is triangle ABC that is blocked by this circle. And the definition of a triangle that is blocked by a circle is only if all the three vertices of a triangle are touching the circle at different points, only then we can say that a triangle is blocked by a circle, exactly like in this drawing. This vertex of triangle ABC touches the circle at point A. This vertex touches the circle at point B, and this vertex of triangle ABC touches the circle at point C. Therefore, we can definitely say that this triangle ABC is blocked by the circle. The length of side AB is equal to A units. The length of side BC equals to B units, and side AC equals to C units in its length. And the radius of this circle OM equals to capital R according to our definition. So whenever we have a triangle that is blocked by a circle, then we can know the radius of the circle that blocks the triangle according to the following formula. Here the radius of this circle that is capital R will be equal to the multiplication of the side lengths of the triangle by each other, that is to say it is A times B times C over 4 times the area of this triangle, triangle ABC. So actually, if we know the side lengths of the triangle, we can find out the radius of the circle that blocks the triangle. Why? Because we can calculate the area of the triangle only by knowing the side lengths of the triangle. So we can actually implement this rule number 1 in our drawing. Why? Because in our drawing we have the green triangle, triangle BDC, that is blocked by this circle. Why the green triangle BDC is blocked by this circle? Because of the fact that vertex B, this vertex touches the circle at point B, this vertex touches the circle at point C, and this vertex touches the circle at point D. Or we can say also that the touching point of the circle and if this vertex is at point B, the touching point of this vertex with the circle is point C, and the touching point of this vertex of the green triangle BDC if the circle is at point D. Therefore, we can definitely say that the green triangle, triangle BDC is blocked by this circle, and therefore we can implement here rule number 1. So I write it down. The green triangle, triangle BDC is blocked or inscribed by the circle, and for that reason you can implement here rule number 1. We define the radius of this circle OM equals to capital R, and the value of capital R, therefore, according to rule number 1, the value of the radius of the circle that blocks triangle BDC, that is to say capital R, according to rule number 1, will be equal to the multiplication of the side lengths of the triangle by each other. That is to say, it is BC times CD times BD over 4 times the area of the green triangle, triangle BDC. Over 4 times the area of the green triangle, triangle BDC. This is according to rule number 1. So the radius of the circle that blocks the green triangle, triangle BDC equals to BC, BC equals to 13 units, times CD, CD equals to the square root of 61 units, times BD, BD equals to 6 times square root of 10 units. Okay, all divided by 4 times the area of the green triangle, triangle BDC. And we already found out that the area of the green triangle, triangle BDC is equal to 39 square units. So we found out the radius of the circle that blocks the green triangle, triangle BDC. That is the answer to the question, because he asks to find out the radius of this circle, and the radius of this circle, capital R, is equal to this expression. Here we'll just simplify this expression by dividing both the numerator and the denominator of this expression by 13, and we get that the radius of this circle that blocks the green triangle, triangle BDC, that is to say capital R, it is equal to 13 over 13 is 1, so 13 will get cancelled, and we left in the numerator with square root of 61 times square root of 10 times 6 over 4 times 39, and 39 over 14 is 3, so it is 4 times 3. In conclusion, we found out that the radius of the circle, that is to say capital R, equals to the square root of 61 times square root of 10 times 6, and 4 times 3 is 12. Here we will divide both the numerator and the denominator of this expression by 6, and we will get that the radius of the circle equals to the square root of 61 times the square root of square root of 10. Here 6 over 6 is 1, so 6 will get cancelled, and here 12 over 6 is 2. Okay. Here we use the algebraic identity that states that the square root of A times the square root of B equals to the square root of A times B. According to this algebraic identity, we'll get that the radius of the circle, that is to say capital R, equals to the square root of 61 times the square root of 10, according to this algebraic identity, will be equal to the square root of 61 times 10 over 2. That is to say, the radius of this circle, this capital R, equals to either the square root of 61 times 10, 61 times 10 is 610, over 2. So the radius equals either to the square root of 61 times 10 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finish with the first method. The next step, I present to you how to find out the radius of this circle according to the second method. In the second method, in the first step, we will do all the things that we have already done in the first method, so I will do it quickly. Here from point C, we will draw perpendicular on AD. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. Here we create quadrilateral ABEC. Inside quadrilateral ABEC we have right angles that the sum of them is 270 degrees. Therefore the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay. And because of the fact that quadrilateral ABEC has 4 right angles, quadrilateral ABEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side EC, but AB equals to 6, therefore EC must be also equal to 6 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE, but BC equals to 13, therefore AE must be also equal to 13 units. And what is the value of line segment ED? ED equals to AD minus AE, that is to say it is 18 minus 13, that is 5. ED equals to 5 units. So we did all the things that we have already done here in the first method. From now on, we will continue with the second method. In the second method, from point O, that is the center of the circle, we will draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O, that is the center of the circle, on chord BC as capital N, and we define the touching point of the perpendicular from point O and AD as capital M. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So the new rule will be rule number 2. According to rule number 2, the perpendicular from the center of a circle towards any chord bisects the chord. So actually if we have a circle, that could be any circle, we know that the center of this circle is at point O, and we have chord BC, that could be any chord, and we have perpendicular from the center of this circle, that is to say from point O to chord BC. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O on chord BC SM. And according to this rule number 2, a perpendicular from the center of a circle towards any chord, that is to say the perpendicular OM bisects chord BC. It means that BM equals to MC. BM equals to MC. Okay, so I can actually implement the new rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON to chord BC. And point O is the center of the circle. So from the center of this circle, that is to say from point O, we have perpendicular on chord BC. And therefore it bisects chord BC. That is to say BN equals to NC. So I write it down. In our original drawing we have perpendicular ON, that is the center of this circle, that is to say from point O to chord BC. Okay, from the center of the circle we have perpendicular ON on chord BC, and therefore according to rule number 2, it bisects chord BC, that is to say BN equals to NC. BN equals to NC according to rule number 2. Okay. BN equals to NC. BN equals to NC. In the next step, we will focus on quadrangle ABMN. On the upper quadrangle ABMN. In quadrangle ABMN, we have 1, 2 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, in quadrangle ABMN, we have 4 right angles, and therefore quadrangle ABMN is a rectangle. I write it down. Quadrangle ABMN is a rectangle But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, we will write so the lower quadrilateral MNEC. Inside this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, quadrilateral MNEC is a rectangle. So I write it down, quadrilateral MNEC. This quadrilateral is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. Again, according to the rule that the opposite sides of a rectangle are equal to each other, we will get that in rectangle MNEC, ME equals to NC. So to summarize what we did until now, according to rule number 2, we found out that BN equals to NC. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to AM. Here BN equals to AM. And according to the same rule that the opposite sides of a rectangle are equal to each other, we also found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. AM equals to ME. Here, side AM equals to side ME. Okay. In the next step, we will extend line segment DA by a straight line until it touches the circle at point F. By doing this construction, we created here chord FD. And a couple of minutes ago, we drew perpendicular ON on chord BC. ON as a perpendicular, it is absolutely a straight line. So ON is a straight line. And according to rule number 1, that the sum of the angles on one side of the straight line is equal to 180 degrees. If you focus on the upper side of the straight line ON at point M, here the sum of the angles, according to the rule number 1, must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to rule number 1. Therefore, this missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of ON at point M to 180 degrees, the missing angle must be equal to 90 degrees. Likewise, if you focus on the lower side of the straight line ON at point M, according to the same rule number 1, the sum of the angles in the lower side of ON at point M must be equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. So actually, we have line segment OM is perpendicular to chord FD. Why? Because OM creates 90 degrees here and here. So we can write down that OM is perpendicular to chord FD. Okay, so I write it down. OM is perpendicular to chord FD. But the perpendicular OM exists from point O, that is the center of this circle. And therefore we can implement here rule number 2. According to rule number 2, whenever you have a perpendicular from the center of the circle, that is to say from point O towards any chord, it will bisect the chord. Therefore, perpendicular OM bisects chord FD. That is to say, FM equals to FMD. FM equals to MD. FM equals to MD according to rule number 2. FM equals to MD. FM equals to MD. But FM, what is the value of FM? FM is equal to FA plus AM. So we can substitute FM by FA plus AM, and it is equal to MD. What is the value of MD? For the drawing, it is very easy to see that MD equals to ME plus ED. ME plus ED. So in conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. Here, line segment AM equals to line segment ME. And because of the fact that the two line segments are equal to each other, we can cancel them out. Okay? And we left only with FA that is equal to ED. FA equals to ED. The line segment FA equals to line segment ED. But we've already found out that ED equals to 5 units. So we can write here that ED equals to 5 units. And from this expression FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Here, line segment FA equals to 5 units. In the next step, we will extend side BA until it touches the circle at point P. Okay, so we created here chord PB, and we have here chord FD that intersects with chord PB at point A. Therefore, we can implement here the old rule number 2. According to rule number 2, whenever we have two chords that intersect with each other, like in this drawing, chord AB intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. Therefore, according to the old rule number 2, we get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So, in our original drawing, we have chord FD that intersects with chord PB at point A. So I write it down. Chord FD intersects with chord PB at point A. The intersection point between the two chords occurs at point A. Repeat again. In our original drawing, chord FD intersects with chord PB at point A. Therefore, we can implement here the old rule number 2. According to the old rule number 2, FA times AD equals to PA times AB. FA times AD equals to PA times AB. Repeat again, according to the old rule number 2, we'll get that FA times AD equals to PA times AB. FA equals to 5 units. AD, line segment AD equals to 18 units. PA is the missing line segment, so we leave it as it is. Times AB. AB equals to 6 units, so we substitute AB by 6. In conclusion, according to the old rule number 2, we found out that 5 times 18 equals to PA times 6. Here we will divide this equation by 6, and we'll get that PA, the missing line segment, equals to 5 times 18 over 6. Okay? Here 18 over 6 is 3, and 3 times 5 is 15. So I found out that the length of the missing line segment P8 is equal to 15 units. P8 equals to 15 units in its length. In the next step, I present to you a new rule and we will implement the new rule in our drawing. According to the new rule, that will be actually rule number 4. According to rule number 4, whenever we have two chords that are perpendicular to each other, we can use a certain formula in order to find out the radius of the circle that contains the two chords that are perpendicular to each other. So if we have a circle, that would be any circle And we know that the center of this circle is at point E. And we have here chord AB. This is called AB. That is perpendicular to chord CD. This is chord CD. And those two chords are perpendicular to each other. That is to say, at the point of the intersection, that is point O, they create between them 90 degrees. So this angle equals to 90 degrees. Okay, all the other angles around point O also equal to 90 degrees. So I write down rule number 4 down. If two chords are perpendicular to each other, that is to say chord FD, if chord AB is perpendicular to chord CD, and they are perpendicular to each other at the intersection point, that is to say it's point O. And the radius of this circle, that is to say EM, equals to capital R according to our definition. Then we can find out the radius of this circle that contains the two chords that are perpendicular to each other according to the following formula. So whenever you have two chords that are perpendicular to each other, you can implement the rule number 4. According to rule number 4, for R square, R is the radius of this circle that contains the two chords that are perpendicular to each other. 4R square will be equal to AO square plus OB square plus CO square plus OD square. I repeat again, whenever you have two chords that are perpendicular to each other, you actually can implement rule number 4, and according to rule number 4, the radius of the circle that contains the two chords that are perpendicular to each other will be, if the radius of the circle is capital R, then the following equation will be true, that 4R square equals to AO square plus OB square plus CO square plus OD square. Okay? So we actually can implement rule number 4 in our drawing. Why? Because in our drawing, we have two chords that are perpendicular to each other, that is to say FD, chord FD, is perpendicular to chord PB at point A. That is to say they create between them at the intersection point, that is point A, 90 degrees. Here this angle equals 90 degrees. And for that, and because of the fact that in our original drawing we have two chords that are perpendicular to each other, we can implement in our drawing rule number 4. So I write it down in our original drawing. Chord FD is perpendicular to chord PB at point A. I'll repeat again. In our original drawing, chord FD is perpendicular to chord PB at point A. And for that reason, we can implement here rule number 4. And according to rule number 4, if we define the radius of this circle as capital R, here OM equals to capital R according to our definition. According to rule number 4, we get that 4 times R squared when R is the radius of this circle will be equal to FA squared plus AD squared plus PA squared plus AB squared. Repeat again. In our original drawing, because of the fact that chord FD is perpendicular to chord PB at point A, we can implement here rule number 4. And according to rule number 4, we get that 4R squared when R is the radius of the circle that contains the two chords that are perpendicular to each other, it is equal to FA squared plus AD squared plus PA squared plus AB squared. Okay, so 4R squared is equal to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18 units, therefore AD squared is 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6 units, therefore AB squared is 6 squared, that is 36. So in conclusion, we found out that according to rule number 4, 4R squared, R is the radius of this circle, it is equal to 25 plus 225 is 250, and 324 plus 36 is 360. So in conclusion, we found out that 4R squared equals to 250 plus 360 is 610. 4R squared equals to 610. Here we will divide this equation by 4 and we will get that R squared equals to 610 over 4. Here we will take out of this equation and we will get that R equals to the square root of 610 over 4. That is to say, R equals to the square root of 610 and the square root of 4 is 2. So R equals the radius of this circle. This is to say capital R. It is equal to either the square root of 10 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finish with the second method. In the next step, let's summarize the lecture. We'll start with the first method. In the drawing we have a circle. The center of this circle is at this point O. Here line segment AB equals to 6 units, line segment BC equals to 13 units, and line segment AD equals to 18 units. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees also. And our mission is to find out the radius of this circle, that is to say the length OM, that is actually capital R according to our definition. The value of capital R. So in the first step we did the construction. That is to say from point C we draw perpendicular on AD, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction we created it for the other ABEC. And inside quadrangle ABEC we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. And therefore quadrangle ABEC that has 4 right angles, it is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to EC. And it is given as an equation that AB equals to 6 units, therefore EC must be also equal to 6 units. According to the same rule that the opposite sides of a rectangle are equal to each other, in rectangle ABEC we have side BC must be equal to side AE, but BC equals to 13 units, therefore AE must be also equal to 13 units. And what is the length of line segment ED? ED equals to AD minus AE, that is actually 18 minus 13, that is 5. In the next step we join points C and D together by a straight line. In this way we created the small right triangle EDC. Then we implemented the Pythagoras theorem on the small right triangle EDC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC, therefore the square of the hypotenuse is DC square. In the right triangle EDC by PT, that is abbreviation for Pythagoras theorem. The square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. Okay. According to the Pythagoras theorem, DC square equals to EC square plus ED square. So DC square equals to EC square. EC equals to 6, therefore EC square is 6 squared, that is 36. Plus ED square. ED is 5, therefore ED square is 5 squared, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. So 36 plus 25 is 61. So we found out that DC square equals to 61. Here we took a root out of this equation and we found out that DC equals to the square root of 61 units. Here the hypotenuse DC equals to the square root of 61 units. In the next step we joined points B and D together by a straight line. By joining points B and D we created this right triangle ABD. And then we implemented the Pythagoras theorem on the right triangle ABD. Here, here PT is the abbreviation for Pythagoras theorem. So in the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. Okay, so BD square equals to AB square plus AD square. So BD square must be equal to AB square. AB equals to 6, therefore AB square is 6 squared, that is 36. So DB square equals to 36 plus AD square. AD is 18, therefore AD square is 18 squared, that is 324. Okay, so In conclusion, we found out that according to the Pythagoras theorem, BD squared equals to 36 plus 324. 36 plus 324 is 360. So we found out that BD squared equals to 360. Then we substituted 360 by 36 times 10. So BD squared equals to 36 times 10. Then we took out of this equation. So BD equals to the square root of 36 times 10. Then we took 36 out of the root. The square root of 36 is 6. In conclusion, we found out that BD equals to 6 times the square root of 10. Okay, so here the property of BD equals to 6 times square root of 10 units. In the next step, we calculated the area of this green triangle, triangle BDC. Okay. Here the squared brackets is the sign for the area. It means the area of triangle BDC. And the area of any triangle, and especially the area of triangle BDC, equals to the base of the triangle times the height of the base over 2. I must emphasize that the height of the base must create 90 degrees with the base. Okay, we choose the base of the green triangle BDC is BC. So we substitute the base by BC times the height over 2. Then we found out the height of the green triangle, triangle BDC by extending side BC. We extended side BC by a straight line, and here we extended side BC, and from point D we do perpendicular on the extended BC. So this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the extended side BC and the perpendicular from point D is F. So when doing this construction, we created quadrilateral ABDF. Inside this quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, this fourth angle must be equal to 90 degrees. And therefore, inside quadrilateral ABDF, we have 4 right angles, and therefore quadrilateral ABDF is a rectangle. Here, quadrilateral ABDF is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DF. AB equals to DF. Here, AB equals to DF, but it is given us the equation that AB equals to 6. So we can write here that AB equals 6. And from this equation, 6 equals to AB equals to DF. We will derive that DF it is also equals to 6 units. Here DF equals to 6 units, but DF is the height to the base BC. And therefore the height to the base BC or the extended base BC equals to 6 units. Again, the height creates 90 degrees with the extended BC, and therefore DF is indeed the height. This angle equals 90 degrees and this angle equals 90 degrees. Okay, now to find the height to the base, we can easily find out the area of this green triangle, triangle BDC. The area of the green triangle, triangle BDC equals to the base BC, and the base BC equals to 13 units, so we substitute the base by 13 times the height. We just right now found out that the height equals to 6 units over 2. So the area of triangle BDC equals, the green triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the green triangle BDC equals to 39 square units. In the next step, I presented to you a new rule, and we presented the new rule in our drawing. According to the new rule, If triangle ABC is blocked by the circle, here we have triangle ABC that is blocked by this circle. Blocked or inscribed is the same. And the definition of a triangle that is inscribed by a circle is that all the three vertices of the triangle are touching the circle at different points, exactly like in this drawing. Okay, so here we have triangle ABC that would be any triangle that is blocked by this circle. The length of side AB is A units, the length of side BC is B units, and side AC equals to C units in its length. And we know that the radius of this circle OM equals to capital R. And then we can find out the radius of this circle by using the following formula. That is to say, capital R equals to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of this triangle, triangle ABC. So we can implement this new rule number 1 in our drawing. Why? Because in our drawing we have the green triangle, triangle BDC, that is blocked by this circle. Why? Because all the three vertices are touching the circle at different points, and therefore we can implement here rule number 1. I'll repeat again. In our original drawing we have the green triangle, triangle BDC that is blocked by the circle, and therefore we can implement rule number 1. According to rule number 1, the radius of this circle that blocks the green triangle, triangle BDC, so the radius OM, that is capital R according to our definition, the value of capital R according to rule number 1 will be equal to the multiplication of the side lengths of the green triangle by each other, that is to say it is BC times CD times BD, if BC times CD times BD, over 4 times the area of the green triangle, triangle BDC, over 4 times the area of triangle BDC. Okay, BC equals to 13 units, CD equals to the square root of 61 units, and BD equals to 6 times square root of 10 units, over 4 times the area of triangle BDC. And we already found out that the area of the green triangle, triangle BDC equals to 14 square units. In conclusion, we found out that the radius of this circle, capital R, that blocks the green triangle, triangle BDC equals to this expression. And that is actually the answer to our question. That is, we asked this question to find the radius of this circle, and the radius of this circle, capital R, equals to this expression. In the next step, we just simplified this expression by dividing both the numerator and the denominator of this expression by 13. 13 over 13 is 1, so 13 will get cancelled, and we left only in the numerator with the square root of 61 times square root of 10 times 6. In the numerator we have 4 times 39, and 39 over 13 is 3. So in total the denominator we left with 4 times 3. 4 times 3 is 12. So in conclusion, we found out that the radius of this circle, capital R, equals to the square root of 61 times the square root of 10 times 6 over 12. Here we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1. So in the numerator we left only with square root of 61 times square root of 10, and 12 over 6 is 2. So the radius of this circle, capital R, equals to the square root of 61 times square root of 10 over 2. Then we used the algebraic identity that the square root of A times the square root of B equals to the square root of A times B. According to this algebraic identity, the square root of 61 times the square root of 10 equals to the square root of 61 times 10 over 2. 61 times 10 is 610. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the first method, then I presented to you how to find out the radius of this circle according to the second method. In the second method, we actually use in the first step, we use all the things that we already found out. We use the same thing, or we did the same thing that we did in the first method, in the first step. That is to say, from point C we draw perpendicular on AD. So this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. By doing this construction, we create a quadrilateral ABEC that has 1, 2, 3 right angles. Therefore, this fourth 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. And therefore, quadrilateral ABEC that has 4 right angles is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6, therefore EC must be also equal to 6 units. According to the sum rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE. But BC equals to 13, therefore AE must be also equal to 14 units. And what is the length of ED? ED equals to AD minus AE, that is actually 18 minus 13, that is 5. Okay, until now we did all the things that we wanted done in the first method. From now on, we continue with the second method. In the second method, from point O, that is the center of this circle, we draw perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC is capital N, and we define the touching point of the perpendicular from point O and AD is capital N. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, a perpendicular from the center of a circle towards any chord bisect the chord. The center of the circle is at this point O. From point O we have perpendicular OM to chord BC. That is to say this angle equals 90 degrees and this angle equals 90 degrees according to our construction. And for that reason, OM is perpendicular to chord BC. And whenever you have a perpendicular from the center of the circle, that is to say from point O towards any chord, it will bisect the chord. That is to say, perpendicular OM bisect chord BC. It means that BM equals to MC. According to rule number 2, BM equals to MC. So whenever you draw from the center of a circle a perpendicular towards any chord, it will bisect the chord. Here, the perpendicular OM from the center of the circle bisect chord BC, that is to say BM equals to MC. So you can implement rule number 1 in our drawing. Rule number 2 in our drawing. Why? Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular ON to chord BC. And therefore, according to rule number 2, it will bisect the chord. That is to say BN equals to NC. I'll repeat again. From the center of the circle, we have perpendicular ON to chord BC. And according to rule number 2, it bisects chord BC. That is to say BN equals to NC. Here, BN equals to NC. Okay. Then we focused on quadrilateral ABMC, ABMN, this quadrilateral, in this quadrangle we have 1, 2, 3 right angles, therefore this fourth angle must be equal to 90 degrees. Therefore in quadrangle ABMN we have 4 right angles, therefore quadrangle ABMN is a rectangle. Okay, quadrangle ABMN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say AM equals to BN. AM equals to BN. In the next step we focus on the quadrangle MNEC. This quadrangle, the lower quadrangle. In the lower quadrangle MNEC we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees, and therefore quadrangle MNEC is a rectangle. Quadrangle MNEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say ME equals to NC. ME equals to NC. So we can summarize what we did until now. According to rule number 2, we found out that BN equals to NC. Then, according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to AM. So we can write here that BN equals to AM. And according to the sum rule that the opposite sides of a rectangle are equal to each other, we also found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here, side AM equals to side ME. And in the next step, we extended line segment DA until it touches the circle at point F. In this way, we created chord FD. A couple of minutes ago, we drew perpendicular ON to chord BC. ON is a perpendicular, it must be a straight line. So ON is a straight line, and we have rule number 1 that the sum of the angles from one side of a straight line is equal to 180 degrees. If we focus on the upper side of the straight line ON at point M, according to rule number 1, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. Therefore, this missing angle must be equal to 90 degrees. Likewise, we focused on the lower side of the straight line ON at point M. In the lower side of ON at point M, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees, as the missing angle. In total, they must be equal to 180 degrees according to rule number 1. So this missing angle must be equal to 90 degrees. So if we found out that OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees, and this angle equals to 90 degrees, therefore OM is perpendicular to FD, to chord FD. Okay, here. OM is perpendicular to chord FD, and whenever from the center of a circle, that is to say, from point O, you have perpendicular to any circle, to any chord, it will bisect the chord. Okay? Here from the center of this circle, that is to say, from point O, we have perpendicular OM to chord FD, therefore it will bisect chord FD. That is to say, FM equals to MD. According to rule number 2. FM equals to MD according to rule number 2. But FM equals to FA plus AM. So you can substitute FM by FA plus AM, and it is equal to MD. Here, MD equals to ME plus ED. So you can substitute MD by ME plus ED. So in conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. Here, AM equals to ME. Here, because of the fact that AM equals to ME, we can cancel out those two line segments because they are equal to each other. So we cancel them, and we left only with FA that is equal to ED. Here, code FA equals to code ED. But ED equals to 5 units according to what we have already found out. So we can write here that ED equals to 5. And from this equation, FA equals to ED equals to 5, we will derive that FA also equals to 5 units. Here. FA equals to 5 units. So in the next step, we extend that side BA by straight line until it touches the circle at point P. So we have here code FD that intersects with code PB at point A. Again, code FD intersects with code PB at point A. Therefore, we can implement here rule number 2, the old rule number 2. Whenever we have two codes that intersect with each other, we can implement the old rule number 2. And according to the old rule number 2, if code AB intersects with code CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So here, now when you are going, we have code FD that intersects with code PB at point A. Repeat again. Now when you are going, we have code FD that intersects with code PB at point A. Okay, therefore according to the old rule number 2, we get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. FA times AD equals to PA times AB. FA equals to 5 units. AD equals to 18 units. PA is the missing line segment, and AB equals to 6 units. Okay? So we found out that 5 times 18 equals to PA times 6. Here we divided this equation by 6 and we found out that PA, the missing line segment, equals to 5 times 18 over 6. 18 over 6 is 3 and 3 times 5 is 15. So we concluded found out that this missing line segment PA equals to 15 units. PA equals to 15 units. In the next step I presented to you a new rule that is actually rule number 4, implemented rule number 4 in our drawing. According to rule number 4, whenever you have two chords that are perpendicular to each other, you can find out the radius of the circle that contains the two chords that are perpendicular to each other, according to a special formula. So here we have chord AB that is perpendicular to chord CD at point O. Why they are perpendicular to each other? Because they create between them at the intersection point, that is point O, 90 degrees. Therefore they are perpendicular to each other. And whenever we have two chords that are perpendicular to each other, you can find out the radius of this circle that contains the two chords according to a special formula. So the radius of this circle is capital R, and therefore we can use the following formula. The following formula is true, that 4R squared, R is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. I repeat again, because of the fact that in this drawing we have two chords that are perpendicular to each other, we can find out the radius of this circle that contains the two chords according to a special formula. That is actually 4R squared. R is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. We actually can implement rule number 4 in our drawing. Why? Because in our drawing we also have two chords that are perpendicular to each other. That is to say, we have chord FD that is perpendicular to chord PB at point A. Those two chords are perpendicular to each other at point A, therefore we can implement here rule number 4. I'll repeat again, in our original drawing we have chord FD that is perpendicular to chord PB at point A. So if we define the radius of this circle OM as capital R, then the following formula will be true. That 4r squared, r is the radius of this circle, equals to fa squared plus ad squared plus pa squared plus ab squared. Repeat again. 4r squared, r is the radius of this circle, equals to fa squared plus ad squared plus pa squared plus ab squared. Okay, 4r squared equals to fa squared plus ad squared plus fa plus pa squared plus ab squared. So 4r squared equals to fa squared, fa equals to 5, therefore fa squared equals to 5 squared, that is 25, plus ad squared. ad equals to 18, therefore ad squared is 18 squared, that is 324, plus pa squared. pa equals to 15, therefore pa squared is 15 squared, that is 225, plus ab squared. ab equals to 6, therefore ab squared is 6 squared, that is 36. So in conclusion, we found out that 4r squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. In conclusion, we found out that 4r squared equals to 250 plus 360. 250 plus 360 is 610. So in conclusion, we found out that 4r squared equals to 610. Here we divided this equation by 4, and we found out that r squared equals to 610 over 4. Here we took a root out of this equation, and we found out that r, the radius of this circle, the radius that we are looking for, equals to the square root of 610 over 4. So it is the square root of 610 over the square root of 4, and the square root of 4 is 2. In conclusion, we found out that the radius of this circle, that is to say OM, the radius that we are looking for, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.